As the last speaker, let me very much thank the organizers for this wonderful meeting and very smooth organization. I have to congratulate them all. And I want to extend my congratulations also to Sai, to some extent. Well, he's also an organizer, but more than that, I think that this conference is, I mean, one example of how effective the work of Sai has been, because not only he has, I mean, created one of the greatest logic network in the world, certainly the biggest set theory network, but now this network is also full of strong researchers which have the ability and the capacity to attract funds and to attract strong people here, and also to organize events like this one. So I think, I mean, I'm very much impressed. And okay, so let's go to this talk. So actually, I have to retract something that I wrote in the abstract, because it should be a model companion for set theory. But it's the right one, so I don't know if so we will come back to this. Okay, so first of all, let's start with modal completeness. So this is a nice model theoretic notion introduced by Robinson, for what I understand. So what is it? It says that a theory is model complete whenever you the theory and the substructure is itself a model of the theory, then it's an elementary substructure. So for example, well, this is a sort of indication of tameness of the theory. Why? Well, first of all, it's implied by quantifier elimination, clearly, because you just have to be a substructure to be an elementary substructure if you have quantifier elimination. Then it is essentially a notion of the theory being complete, because maybe the theory is not complete because it could have many different minimal models. But if you fix a model and the diagram of atomic formula of the model, then it's fine. From all the supermodels, which are models of T, are elementary supermodels. And then it also has a nice axiomatization. When you have a model complete theory, well, you know that you just have considered the pi2 fragment of the theory to get a set of axioms for the theory. Okay? And, well, the bad issue about model completion is that if you have column function for the existential formula, it is model complete. Why it is a bad issue? Well, because you can always add column functions. So you start from a language L and the theory T, you expand the language with column function, you have a conservative extension of T, and now the conservative extension is model complete. And why it is bad? Well, because if you want the notion of tameness, well, it says every theory modulo passing to a conservative extension becomes tame. Okay? So what I would retain of this notion of tameness that you get from model completeness is how non-constructive are the column function that you are going to add. Okay, so you will have them by the axiom of choice, but do you really need the axiom of choice to find this column function? If this column function can be given by some much simpler argument, then the theory, it is to some extent tame, because it is true that you are expanding the language, but you expanded it in a tame way to the axiom of choice. Okay? And these are key characterization of model completeness. Okay, so a theory is model complete if and only if every model of T is existentially closed. This means it's a sigma 1 superstructure, a substructure of any of its superstructures in the same language. And other fact is that whatever sentence you take, well, you don't have quantifier elimination, but you can eliminate all quantifier up to a universal quantifier. So it's not quantifier free, but almost quantifier free. Okay. And point 2 is one of the reasons why I got interested in modal completeness, because this is very much reminiscent of what happens with bounded forcing axioms. Bounded forcing axiom says that H omega 2 is sigma 1 elementary in the superstructure. So to some extent, the ZFC plus bounded forcing axiom is, well, the theory of H omega 2 plus bounded suggests that the theory of H omega 2 is model complete. Okay. And what is the key example which I think drives this definition is the notion of algebraically closed field. Well, it has quantifier elimination, so it clearly is model complete. Okay. Okay. And now we pass to the other notion, the notion of model companion. So the idea is the model companion of T is well, okay. Now I call S. I switched letters. Maybe I should have stick with S and L theory and T the model companion, but unfortunately I did not. Okay. So those are two theories which have different axiom, different model. It is well possible that any model of S is not a model of T, and any model of T is not a model of S. But there is a strict relation between them. What is this? What is the relation? Well, you take M, which models S. Then you can expand it to N, and then you can expand this to another M prime, which models S, and so on and so forth. So you can always take a structure which is a model of S, expand it to a structure which is a model of T, take a structure which is a model of T, and okay. And well, okay, up to here there is nothing special, but you ask that the model companion is a model complete theory. Okay, so and now this is the standard example to grasp what the concept captures. So for example, you take T, the theory of commutative rings with not zero divisors, and you may even assume that this theory is T plus I'm not a field. Okay, well, and then you get that the theory of algebraically closed field is the model companion. Why? Well, you take any model of T. This is a ring without zero divisors, so you can expand it to a field F because you add all the fractions, and then you expand it to an algebraically closed field K. Okay, and then so this is a model of S, and then again, you can make K of T, and you get a model of T. Okay? So those two theories have different axioms, but there is a strict relation, and the theory S is the nice one because it has this reflection property. Every superstructure is a sigma 1 superstructure. Okay? Also, a thing to notice is that the different theories can have the same model companions. For example, I could have taken S to be the theory of fields, and I would have ended up with the same model companion. Okay. And okay, so we take this theory S, and what happens is that if the theory has a model companion, then it's unique. So there can be different theories that have the same model companion, but there cannot be two distinct theories which are model companion to the same. Okay, and to understand whether it's a model companion, you have just to look to the universal part of the theory. So S for all. Okay, just the universal formula of the theory, and then try to sort of saturate the models of this S for all to grant that they will become existentially closed. Okay, and then a set of axioms for this theory is for the model companion is always given by the for all epsilon fragment. This I was already saying before. Okay, so how do you get to the model completion? Well, you do exactly the same pattern you do to prove the bounded forcing axiom. So you start with you start from your model M of S. Well, there is an existential formula which is not realized here. You pass to M prime, which realizes the existential formula. There is another existential formula which is not realized here. You continue, and at the limit stage, you take the direct limit. You continue, and in the end, you will end up with a formula M such that for all x, if you take an existential formula in parameter x, there is a solution, and you get your model of T. Okay? Exists fragment of T will be also its set of axioms. Okay, and now we come to the issue of the model companion or a model companion. Okay, actually in the abstract I wrote a false statement that I said that no recursive extension of ZF as a model companion. Actually, ZF as a model companion, so any recursive extension of ZF as a model companion. But this model companion is very stupid because it is a theory. I mean, what is this theory as saying? It is saying that the epsilon relation does not have loops. So it's not even saying that the epsilon relation is well-founded. It's saying I cannot find a finite set of elements such that the first belongs to the second, which belongs to the third, which belongs to the fourth, which belongs to the first. Okay, so it's a theory of asserting that that the epsilon relation does not have loops. Well, we do not learn much about sets by studying this theory S.
What if you look at ZF minus relation?
I guess in this case it's not even clear that it has a model companion. So what is the problem? The problem is that we are used to consider bounded formulas as simple, okay? But to do so, we resort to the trick of adding the bounded quantifications, okay? And take the bounded formula but there is a problem that syntactically, when we quantify over bounded theory, those are true quantifications. So this formula, which is a quantifier free, well, from the point of view of the syntactic complexity, is a pi2 formula, okay? And for us, it should instead be a delta 0 formula, which is much less. So we have to expand the language in order to solve this problem. So what you do, well, the simplest solution is we add a predicate for every bounded formula, and we add the axiom stating that the bounded formula holds if and only if the predicate holds. Okay? And now we study this. And this is the theory for which we are going to look at the model companions, okay? So you see already, this example is illuminating because it's saying that this notion of model completion is a model companion is very much sensible to the language you choose to study your theory in. So you have to choose the right language in order to get full information. Okay, and now comes the point where I started to, I and Giorgio, because actually it is Giorgio Venturi who realized that this notion of model completeness and model companion is very much tied to how we look at the generic multiverse. Okay, so what is the generic multiverse? Sloppily, you can define it as the initial segments of the universe in a generic extension, okay? And I want to take the initial segments, but I want to take them big enough so to be able not to lose information about the forcing. So this is why I'm asking that that I take h kappa Vg, but I ask that kappa is a regular cardinal in Vg, and the forcing is of h kappa. Why? Because if I take smaller h kappa, then I will not be able to recognize by which forcing I have obtained that h kappa. Because I will not be able, for example, the generic will not be a subset of h kappa. Okay? Okay, the problem with this definition is that there are no V generic filters. Okay, so if you are formally correct, well, what you end up having is just enumerating all the h kappa for kappa regular cardinal in V. Okay, so you have to, if you want to make your study at least meaningful, you have to change your definition. The standard solution is this one. You take a countable transitive model of ZFC, and then you relativize everything to this countable model. Then you have the generic filters for any poset in the model, and you can define the generic multiverse according to this definition. Okay? And everything works well. But what I want to do, it's not strictly necessary, but okay, and another observation is that you have this fact that h kappa mg is a substructure of h delta mh if and only if kappa is less or equal than delta, and mg mh is a generic extension of mg. Okay. But the way I want to look at the generic multiverse is this other option, which is you take the names for elements of h kappa of the generic extension. So those are those B names such that they satisfy the formula that their transitive closure has size less than kappa. Okay. So this is giving you a canonical representative of the structure h kappa in the generic extension. Okay, and now you mod out by a complete Boolean by a ultra filter on B. Okay, and you let G vary over all possible ultra filter, and you take these quotients. Okay. What happens is that now these models are never well founded, okay, because G is not V generic. It's just an arbitrary ultra filter on the stone space. But the first order theory of this model is ruled by the forcing theorem, so essentially what holds here is much like what you would get if G were a generic filter. Okay, and maybe since it could be the case that yes, okay, which means that we have a bit of okay. So here I go very fast. We take a stone space of a Boolean algebra. This is space of ultra filters. You have a space of Klopen sets which are given by the ultra filter, which you fix an element of the Boolean algebra. The ultra filter to which it belongs are the Klopen sets, and you have an isomorphism, natural isomorphism between the Klopen sets and B, and you can characterize the fact that B is complete by the equality of Klopen sets with regular open sets. In general, Klopen sets are different from regular open sets, but if your Boolean algebra is complete, you have this equality. Okay. And what is the semantics? Well, you take a B-valued model. What is that? Is a set together with relations. The requirement is that now you evaluate your formula in the Boolean algebra and not as true or false. So you have a relation of equality which assigns to every pair of elements in the structure a Boolean value stating how much they are equal, and then for any relation symbol you have a value of how much the relation holds for this tuple. And well, you want the rules of equality for first order logic to hold, so you are forced to require that any element is equal to itself with Boolean value 1, that the relation of equality is symmetric, it is transitive, and then you have to ask that if you substitute equal elements into a relation, you will get that the relation holds for the other. Okay? And now you define the semantics in the standard way. Okay. Now you will use the Boolean operation to establish the propositional connectives, and it's convenient if that your Boolean algebra is complete to interpret the quantifiers. And you have the soundness theorems. So if you have that the formula is derivable from a theory, then to every element of the theory will give value B to the formula. And the completeness theorem is automatic because B is a complete, 2 is a complete Boolean algebra. But what is interesting is when you go to the quotient, you define two elements to be equal modulo the ultrafilter if the Boolean value that they are equal belongs to G, and then you can also pass to the quotient the relation symbols. So you define on the equivalence classes the relation holds on the equivalence classes if and only if the Boolean value of the relation of some representatives belongs to G, and the semantic is made up so that this is well defined. And well, the problem is that you paying attention, you will end up having Boolean valued models which are not well behaved. In order to be well behaved, you need this maximum property. You need that whichever existential formula you compute, well, the Boolean value of the existential formula is not a sup, as it is in the definition, but it's a max. So there is some name in the model for which the Boolean value of this is equal to that. Once you have this theorem, or the Boolean valued Losch theorem, which says, well, this is the exact analog of Losch theorem. It says a formula holds in the structure if and only if the Boolean value of the formula belongs to G. Okay, and how do you prove it? By induction. For atomic formula, it is by definition. For the Boolean connectives, you use the fact that the law of Boolean algebra grants it. And for the existential formula, well, in one direction it's easy, and for the other direction you use the maximum property. But then, I mean, turning it around, it's the forcing theorem. It says A is below the Boolean value of a formula if and only if whenever you pick an element of the open neighborhood given by A, you have that the quotient structure satisfies the formula, or weaker property, which is what is used all the time in forcing. You just have to check the property for densely many elements in this neighborhood, not for all of them. Okay. And well, now you see that this definition is the right generalization of Losch theorem, because if you take the px valued model, well, the standard ultra power you take with the ultrafilter on px are just Boolean valued model according to our rules. The quotient of Boolean valued model according to our rules. Okay? If you have an ultra power of a model of M, then this map is elementary. Well, it doesn't really matter. Okay, and then this is the model of set theory we are used to work with. Well, we take all, what is an element of this model? It's a function from this class into the Boolean algebra, a set size function from this class to the Boolean algebra. And then we can define, sorry, here there should be a parenthesis. And then we define this stuff there. Okay, those are the relations that are fine to define the epsilon relation and equality relation. Okay. And this is it. And yes. Okay, so now you know what this is. It's clear. And you know what this is. which before maybe you had some doubts, but now it's clear what it is. It's just a quotient. Okay, which morphisms should be considered in the generic multiverse? Well, we like the morphisms induced by forcing extensions or the algebraic morphism. And actually the two things are the same. And you end up with this other if and only if this number is smaller than this other as ordinals. If and only if this Boolean algebra is a complete subalgebra of this other, and if and only if this ultrafilter is the trace on B of this other ultrafilter. And when this occurs, well, this occurs if and only if this map is a well-defined morphism. And the key fact is that it not only preserves the epsilon relation and the equality relation, but it also preserves all delta 1 properties, and actually it preserves all bounded formulas. So it's suitable, this setup is suitable to study set theory in the language I have defined before. Okay, and now what is the what will happen? Okay, that if we take this type, whenever we are able to put this structure inside our generic multiverse, this occurs when this number is smaller than the size of B, or smaller or equal than the size of B. Okay, then we have that this structure is existentially closed. Well, this is essentially the Schoenfield's absoluteness, okay? Because Schoenfield's absoluteness tells us whenever you go to a forcing extension of the ground model, every sigma 1 formula in real parameter which is true in the forcing extension is already true in the ground model. So this is saying this structure is existentially closed, okay? So it's a very strong indication that this theory should be model complete. And also another fact is whichever element in our generic multiverse we take, well, we can also always go to a larger element which is of this form. Why? Well, this is, I mean, I also have this, I don't know if it's worth, well, maybe you can go to B. You just collapse, okay? You take your element of the generic multiverse, well, this kappa is a certain element, you go to a large enough delta, and you collapse. Well, we have that B completely embeds into this forcing notion, and we can assume that B is a complete subalgebra of C. We take any the ultrafilter G on B and we extend it to a ultrafilter C on H. And here we now get that every element of H kappa B has become a countable object in V of C. Okay? And this delta, because of the property of this forcing, has become the first uncountable cardinal. Okay? So what you get is that H delta C mod H is actually the H omega 1 of the generic extension. Okay, and your map is defining an embedding of this structure inside this structure. Okay. Okay, and so we have that every model of this generic multiverse embeds into one of this form. The one of this form a sigma 1 existentially closed class of model, and clearly every model of this type embeds into an element of the generic multiverse itself, so we have no problem. And well, we still need the model completeness, but this is what Woodin's generic absoluteness gives us. Woodin's generic absoluteness tells us that those models always have the same theory of H omega 1, because you cannot change the theory of projective sets using forcing, assuming large cardinals. So these models are always the models of this theory. Okay, so it seems we have done. We have found the model companion of set theory, but we have found the model companion of set theory just with respect to the structure which are in the generic multiverse. Okay? Okay. So, are these two theories really model companion? Well, not really, because the point is that the generic multiverse is not picking all the possible models of the theory we are interested in. It's just picking the models which sorts out by applying the forcing method. There are many other models which, well, who knows, but there could be other models which are not popping up using the forcing method. Okay. Well, the main problem, because why this theory is not model complete, is that, okay, the first problem is solved. It is possible to show that whichever model you pick of some initial fragment of V, okay, you will be able to embed into a model of this form. But the second problem is not solved, because this theory is not model complete. So we have to make our second syntactic stretch of the theory of set theory, okay? So we have to add more predicates, so that now our T prime is model complete and has the same pi1 theory of V. So what we do, well, before we were forced to add the predicates in order to have something meaningful. Otherwise, we were just talking about nonsense. This time, we are sort of doing the trick that is, given a theory T, allows us to enlarge to a theory T prime, which is model complete. So in this case, it is just to evaluate how much of a trick are we doing. Is it a good trick, or are we doing something unnatural? Okay. What we do? Well, we consider second order number theory. And clearly, this theory is interpretable here. And because this class is a subset of H omega 1, and any set definable here is definable here. And also this converse hold, but now you have a switch of quantifiers. So pi1n sets, so the sets which are defined by pi n formula in this structure corresponds to, okay, well, this is descriptive set theory. Well, you can code any element here inside power set of n, assigning to any A the graph of the transitive closure of the singleton of A, identifying H omega 1 with a pi11 subset of 2 to the n. Okay? And this map code is defined by an absolute operation. It's probably a delta 1 property. Okay? And using this map, you take a set which is sigma 1n into 2 to the n, and you obtain that it's sigma n minus 1 definable in H omega 1. And conversely, if you take a sigma n definable subset of H omega 1, you apply the map, and you get that the image of A under the map is sigma 1n plus 1. So you have increase of 1 cardinal. Okay. And why the theory of H omega 1 is not model complete? Well, because we have universal sets for projective sets. So you remember, a theory is model complete if every formula is equivalent to a universal formulas which are sigma 1 n plus 1 complete, and they cannot be pi11 definable. Okay? So what we do? Well, essentially the solution is we throw in all these formula as new predicates. But why this is a legitimate move? where those predicates are universally bare. What does it mean that they are universally bare? It means that forcing is not affecting their behavior. Okay? And essentially, you get that universal bare gives a sharp bound between the subset of 2 to the n, where the theory of those subsets is not affected by the axiom of choice, and those subsets instead which exist in general just appealing to the axiom of choice. Okay? Well, here are some examples of universally bare or non-universally bare sets. Well, the problem is if you assume V equals L, there are projective sets which are not universally bare, but if you assume enough Wooden cardinals, then every universally bare set is determined. Okay? And projective set becomes universally bare. Okay, so this is what we need from Wooden's generic absoluteness. If you have enough Wooden cardinals, every set in L of R, every subset of R in L of R is universally bare, but you can even force a model, which I would say is the canonical model, such that whichever set of reals you compute in the Chang model, together with predicates for all universally bare sets, well, this set of real will be by itself a universally bare. Okay? In this case, it's not an outward theorem, so you have to force the existence of such a model. But I think it's a safe assumption to assume that we satisfy this hypothesis. Okay, and now you take the second expansion of your language. You add predicates for all universally bare sets, and now this model complete. Why? Well, because you have essentially you have quantifier elimination. What happens? You take the extension of a formula, you pull it back using your coding function. This gives you a universally bare set, because any set which is definable in H omega 1 with this predicate is universally bare, because it belongs to this model. So your formula now becomes this pi1 formula. The set which was the extension of an arbitrary formula now becomes this pi1 set. So okay, so we have shown that every formula, the extension of every formula is equal to the extension of a pi1 formula, which means that this theory is model complete. Okay, now it's easy to argue that the theory of the universal theory of V has, or the theory of V has as model completion this theory T0. Okay, T0 is the theory of V, and T1 is the theory of this structure, and it's clear that T1 is going to be the model companion of the theory of T0. Okay, well, the first point is that you still have the Levy absoluteness. It's not hard to check that the same proof more or less works. So they have the same pi1 theory, which is a necessary prerequisite in order to have model companion. And then if you have a pi1 theory, if you have more theories, well, two models which satisfies the same pi1 structure of the other, you can extend. Okay, so this is called resurrection. If you have, so if they satisfy the same pi1 sentences, it means that M is a sigma 1 elementary in N. Then in this situation you can expand N to M prime. Sorry, here it's nothing, it's just a substructure, so that here you have full elementary. Okay, so this means that the condition that you can take a model of T0 and embed into a model of T1, and take a model of T1 and embed into a model of T0, you can do it. Okay, and if you don't want to use this strange model of set theory which you obtain by forcing, then you just add the universally bare predicates which belongs to L of R, or even just the projective predicates, and you can run the same proof, and you end up with having the model completeness. Okay. And I mean, I have dealt in details the case of h omega 1, but actually we can stretch it also to h omega 2. In this case, we have to take the theory, the pi1 theory of h omega 2 with parameters in h omega 2. We have to assume forcing axioms, and well, it's better to say conjecture rather than theorem, because I never set up and wrote down the full details of, but I'm sure that if this theorem is false, I will, well, I just twist it a little, I add some predicates which I like, and then the theorem becomes true. So for the moment, I state it like that. Okay, and actually this is just because I mean, this is a whole family of theorem that you will have whenever you will have an axiom granting that this theory is generically invariant. Okay, with respect to forcing, which preserve the delta 1 property of this model, then you will be able to establish that the theory of this stuff is the model companion of the theory of V with some extra predicates, with the good parameters. Okay, and this is the two books where you find all the, I mean, you see there is no, all the hard work is done by Budin essentially, and then you pick some standard things in model theory and you cook it up. Okay.